All right, we are live. So welcome back everyone to another Quantum Matter seminar. It's been a while since the last time because we took a long break after the summer. We're still working out the schedule, and it's a pleasure for me to uh, introduce Joshua Heath from the University of Connecticut and Nordita, who's working in the group of Sasha Balasky. Before joining, he was a postdoc in Kevin Riddell's group in Boston College. He got his PhD in 2021 from Dartmouth. And with this, I want to um, um pass the mic to Joshua, and Josh, take it away. Thank you.
Okay, thank you, Professor Figman. So today I'll be talking a little bit about some work I did on my previous postdoc at Dartmouth College. So as Professor Figman just said, basically all of this work I'm going to be talking about is not going to be at my current institution. I just began about a month and a half or 2 months ago. And so right now I'm in a superposition of states between Nordita and Nordic Institute for Theoretical Physics in Stockholm, Sweden, and University of Connecticut in Stores, Connecticut, where I am now physically. You can see these in the background here. And here's Nordita, and here's University of Connecticut in a superposition. But today I won't be talking about any of my work with Professor Balatsky. I'll instead be talking about my work that I did in my previous postdoc, where I was from the end of 2021 to the middle of 2024. And this work is universal scaling laws installing and tracking superconductors, and this was work done at Dartmouth College with Professor Rufus Boyack, who can be seen here. So in this work, everything I'm going to be talking about today is completely on the archive. Here's the archive number. It's currently under review at Physical Review Letters. So if you have any questions or if you can't see anything, just please unmute yourself because I won't see a hand up, I think. Okay. I'm going to move a little cold, so I might cough a little bit. So what we'll be talking about today is motivated by this idea of high temperature superconductivity. So why are high temperature superconductors different and why they're special? So here we see a plot of the critical temperature Tc versus the year of discovery of the material on the x-axis. So we see superconductivity was first discovered around 1900 in mercury, and then we discovered lead and niobium. And if we follow the dark green line, this follows the line of materials that follow BCS theory or conventional superconductors, which have just conventional Cooper pairing from this weaker electron-phonon interaction that's well described by this well-known BCS theory up to here, MgB2. Now, along with many different materials, especially some more recent materials, around 1986, 1987, it became known that some materials that were composed of carbon and oxygen, these cupric materials, actually had a much higher Tc. So, and these are represented by these blue diamonds here. And they're much higher than this dark green line described by BCS theory, and these are known as the cuprates. Now, the cuprates don't really follow a cohesive picture, basically, underlying theory, a well-known theory. The underlying glue is often, and some of the details of the glue, now holding these electrons together in a Cooper pair is often differ depending upon which material you look at. So there's no universal, easily understood universal phenomenon that ties all of these guys together like it ties all of these dark green ones. And this has motivated some people to turn to Leo Tolstoy to actually describe these materials, these cuprates, when it's Anna Karenina principle. And what does Anna Karenina principle say? Well, basically modeling after the first line of this famous novel, people might say that all conventional superconductors are alike, and all unconventional superconductors are unconventional in their own way. So all conventional superconductors in a sense of BCS, superconductors described by BCS theory, all described by this well-known theory, while all conventional superconductors don't really have this nice universal picture and are all a little bit different in their own way. So Rufus and I oppose the Anna Karenina principle, and many people before us opposed the Anna Karenina principle in the sense that we want to understand universal behavior That's applicable for both conventional and unconventional superconductors. So this has motivated people to actually look more empirically, experimentally than theoretically, and this led to the famous work of Christopher Holmes in 2004. So what Christopher Holmes found was that if you plot the zero temperature superfluid density on this y-axis, and you plot the normal state conductivity times Tc on the x-axis, we're looking at these different classes of materials denoted by these different colors here and these different shapes. If you plot them on the same line, and then if you plot them all on the same plot, they all form a straight line. So once again, this is the T equals 0 superfluid density and the product of the normal state DC conductivity and the critical temperature, sigma Tc. And for these class of materials, they all form the linear line. So this is known as Ohm's law or Ohm's scaling. And would seem to be something that, okay, all the cuprates seem to follow. Now, the catch is that it was a little bit too good, and it works for systems well beyond the cuprates. So it works for the pnictides, it works for the fullerenes, the elementals, the organics. If you plot them all on the same graph, they all fall in a straight line. So they all obey Ohm's scaling. So what we want to ask in this talk is what is the physical origin of Ohm's scaling, this linear relationship between a T equals 0 superfluid density and normal state conductivity times Tc. At first, it was proposed as something that might be universal to help us understand the cuprates, but it's understood in many, many other superconductors as well. So it's not just cuprate specific. And our proposal is that Ohm's scaling is basically a byproduct of non-Galilean invariance and a breakdown of Galilean invariance. By this, I mean there's some fundamental scattering mechanism, microscopically, we'll talk about, either from electron-phonon scattering or electron scattering off an impurity, that would break the underlying Galilean invariance of the system, and that ultimately will be a necessary but not sufficient condition for Ohm's scaling from the BCS limit to the more strongly coupled electron-phonon limit. And this has nothing to do with a high TC, so there should be a high TC here. It has something to do with a very high TC or an exotic pairing mechanism or so on. So it's applicable to many different superconductors because it's has something to do with a very high TC. And as I said, basically we'll be using as a case study for this, looking at the electromagnetic properties of these electron-phonon superconductors described by Eliashberg theory. And we'll be doing a combination of a theoretical and numerical approach, looking at these arbitrarily strong interaction strengths and arbitrarily purity concentration strengths as well. And what this implies is that these universal features that we'll see in these electron-phonon superconductors challenge colloquial notions of conventional superconductivity. In a sense, what we'll find is that really what we mean by conventional in this sense is something that would be even more universal than BCS, and that would be this Ohm's law. So Ohm's law really defines what we mean by conventional in a sense. So to rewrite the Anna Karenina principle, we can talk about the Ivan Veen principle now from the lead character, Ivan Veen from the lead character of Vladimir Nabokov's novel Ada Oradora, which sort of lampoons the first line of Anna Karenina. And we will say that all Galilean invariant superconductors are more or less dissimilar, and all non-Galilean superconductors are more or less alike. And like I said, this idea of this breakdown of Galilean invariance in a system is intimately tied with Ohm's scaling. So our contribution will then be that Ohm's scaling unifies nearly all non-Galilean invariant electron-phonon superconductors. Ohm's scaling isn't just for high TC. Any questions at the moment? Okay. So basically, like I said, we're looking at Ohm's scaling in a context of these electron-phonon superconductors. The important thing is that there is no underlying theory now, existing theory, for Ohm's scaling beyond the dirty BCS limit. So we are really the first to actually go through this problem, and what I'll show you is that we completely solved the problem of Ohm's scaling these in Eliashberg superconductors from the electron-phonon coupling going from 0 to infinity. We basically solved the problem. So now, first of all, let's try and understand a little bit more about this high TC and why this is special. So we know that in these cuprate materials, so why did we need it in the first place in this idea of home scaling? So just zooming out a little bit and before we go into electron-phonon superconductors. So in these high TC materials, a lot of people probably in this audience have probably seen this. When we plot the temperature versus hole doping, we've seen it as this very exotic cuprate phase diagram. So as we tune the hole doping, we might go from some antiferromagnetic order to the famous pseudo gap order to ultimately the strange metal phase. And the strange metal phase seems to be normal phase seems to be connected to this very high superconducting dome. So people thought, especially on Zanen, thought there was some connection between this very high TC and this non-Fermi liquid strange metal phase. So what's strange about the strange metal phase is that first of all, there's no quasi-particles. So a regular Landau Fermi liquid would have well-defined quasi-particles because its resistivity never goes T squared. Whereas in the strange metal phase, the low frequency peaks of the optical conductivity were shown to have a width and order temperature. So this is inconsistent with a dressed particle or quasi-particle like picture. So not a Fermi liquid, it's a non-Fermi liquid. You can't adiabatically connect the interacting eigenstates to the non-interacting electron gas. Okay, so then was shown suggested by Hartnell and Koch that its scaling of the transport quantities are inconsistent with Fermi liquid theory, as with conventional quantum critical scaling. So it's a very non-trivial quantum critical phase. More recently, some nice work of Patel shown that this linear T resistivity is explained via 2D fermions coupled to quantum critical scalars. So this might lead to some Yukawa SYK or SYK-like model to try and describe the microscopics. And as I said before, experimentally, people were trying to look at home scaling, looking at this linear relationship between a zero temperature superfluid density and a normal state conductivity times Tc. So home scaling was really tried to be was something that people tried to use, like I said, to have like a cohesive universal picture. Fermi liquid theory doesn't work. For the normal state, BCS theory doesn't work for the superconducting state. So the scaling law between the zero temperature superfluid density and the normal state conductivity seemed to be something that was universal. The problem was, as I said before, is that it's not unique to the cuprates, but it's actually a little bit worse than that. Home scaling even works for BCS systems. So here, this is my own plot, and we can see that if we plot the zero temperature superfluid density on a y-axis, and on x-axis we have the normal state conductivity times Tc, and we change the value of tau, which is a transport scattering time, or scattering time, and that's noted by the color here, we see we have the emergence of we go from home scaling to this plateauing regime where home scaling is violated. So here I have the zero temperature gap to normalize everything and make this unitless. And basically the blue here means 1 over tau is very, very big. So tau is very small. So the mean free path between these electrons is very small. So there's a lot of impurities in the system. So we see when there's a lot of impurities in the system, we actually have in this linear scaling between the superfluid density and sigma Tc. I normalized by the plasma frequency squared to just make this guy unitless. And then as we decrease 1 over tau, and we go to cleaner and cleaner, and then we have this plateauing regime. So this plateau is very intimately connected to the superfluid density going to unity. So, and a very clean system. So the superfluid density goes to 1. The normal state conductivity it's described by Judah theory. So tau will be diverge. So sigma will diverge. And then we have just a complete breakdown of home scaling now. So home scaling works in a dirty BCS superconductor. Now, this is actually technically really not new physics. It's just known even from the 1967 work of Sangbo Nam. So what Sangbo Nam showed was that the superfluid density at T equals 0 is directly proportional to the zero temperature gap delta naught times tau, transport scattering time. So I can just multiply and divide by Tc here. And we know in this BCS superconductor, delta naught over Tc is a constant, it's 1.17 or so. Tau is directly proportional to sigma. And then we have TC times sigma. So home scaling the BCS system follows directly from dirty BCS theory. So BCS theory and the limit of very large impurities. And this formula only works in a dirty limit because otherwise this would be larger than 1 and the clean limit, and then it would not make sense. So this is only a dirty limit formula. So home scaling works in a dirty limit in BCS theory, and by definition, therefore, in the weak coupling limit. However, note that BCS home scaling cannot explain what we see in the cuprates. So the cuprates differ for two reasons. One of course is that it's a strong the cuprates are strongly interacting. BCS theory is a weakly interacting theory. So that's one knob we can't really tune in BCS theory. We can tune it in these cuprates. It's a very strong interaction, but on BCS theory. And also the experiment I showed you before that Holmes did, Chris Holmes did for the zero temperature superfluid density and the normal state conductivity times TC was more in the cleaner limit. So in no way can we really describe what we see in the cuprate systems, this home scaling with the home scaling we see in the BCS system. So our proposal is that really home scaling, sorry, not to say home scaling, is more universal in both BCS and cuprate physics. So it's more universal in both in a sense. And to understand this a little bit better, we have to add like this another knob to tune and go a little like one step beyond BCS theory. So what we'll do is we'll go to Eliashberg theory and consider some more dynamical electron-phonon coupling to really understand more intimately what's going on in these systems and what it means to what really leads to home scaling. Any questions so far? Okay. So the underlying idea of this dynamical electron-phonon coupling can really be understood, say, from the context of some older work by Eliashberg, as I'll show in a second, but also from a nice review by Marsiglio and Carbat. So in this review, and they basically show this diagrammatic, and this pictorial or schematic picture of what's going on in these systems and how it's different from BCS. So first, if we have a more realistic material, and then if we have some electron in the lattice, these heavier ions are going to be attracted, positively charged ions will be attracted to the negatively charged electron. So we'll have some attraction towards the electron, and then this will create a cloud of negative, positive charge, and the electron will see it and go towards. But in a realistic material, these ions are heavy, and the electron will still see this positive charge here once this little electron has already moved away. So things are not instantaneous here. Basically, we have more of a dynamical coupling between the electrons and phonons and a dynamical theory of superconductivity, basically. So in the context of this theory, which is known as Eliashberg theory, which was known as ETH later on, now the gap, delta, and will have to be solved self-consistently. In addition, we have to solve these two equations in these simplified models. So I consider particle hole symmetry, a local self-energy in one band to just make everything simpler. And in this simple version, we have these two self-consistent equations. So the green one here is delta, the gap, is a function, and I write it on the imaginary frequency axis, in terms of the Matsubar frequency, and Z. Z here is related to the normal component of the self-energy. So you can think of that being related to the quasi-particle weight. So here we sum over the Matsubar frequencies, and you've seen that it's related, this delta at the mth Matsubar term is related to all other Matsubar gaps at other Matsubar terms. And this lambda here denotes this electron-phonon coupling strength in terms of the Einstein frequency. We'll strictly be considering an Einstein phonon model for simplicity and for much deeper physical reason that we'll go on to later. So what's useful about this Eliashberg system, first of all, it's easier to solve on the imaginary axis. So what we'll do numerically is we can suggest some initial form for the gap function for each Matsubar term, like just even an array of ones. And then we can iteratively solve these equations going down and iteratively solving until we have convergence of delta and z. And if we wanted to go into the real axis and actually get the physical, the Eliashberg analog of, say, the BCS gap, and that would be the gap edge, then we can just analytically continue to the real axis and then get the real frequency delta and z. We won't be doing that here because we can calculate everything we want on imaginary axis. And I'll show that later. What's also nice about Eliashberg theory is that it contains the details on the underlying phonon propagator. So, for example, different materials might have a different phonon behavior, and that can be incorporated into then delta and z. Whereas in BCS theory, we wouldn't have this. So in Eliashberg, in this, all contexts will be strictly considered an Einstein phonon model, which is given, this lambda, this Eliashberg function is given here. And the electron-phonon coupling strength is dimensionless electron-phonon coupling strength is parameterized by this lambda. So in a realistic material, lambda is usually limited by some upper threshold, some people believe. So for example, lead might be around 1. I think aluminum is about 0.43. The hydrides people think might be around 4 if it could be described by this model. But in general, people theoretically could consider any value of lambda. So we'll define lambda large, small, and 0.5 as weak. There's some very nice work by Frank Marsiglio on that has gone over this. We'll define lambda large and 4 as strong. And later on, we'll take lambda going to infinity, which is a special case, is asymptotically strong. So once again, we aren't really concerned about like describing a realistic physical material at this point with lambda going to infinity. What we really want to just understand is by going from taking lambda going to infinity later, is what universal properties we can glean from this calculation. So when lambda goes to infinity, we get universal behavior. Yes, so these are the Eliashberg equations we'll be working with, which is, like I said, a step beyond BCS theory. As I said before, we'll define this on the imaginary axis, the Matsubar frequency axis. And if we just numerically solve these solutions, then we can plot them, and then we can save them and grab them later when we actually want to calculate some physical quantity, like the superfluid density, which we'll do in a second. So we can plot delta n versus omega n, and we can go from lambda very small, say 0.3 to 100. So this is using my own code for safely solving these self-consistent equations for any lambda that I also use for the paper. And we see we have this Gaussian-like distribution, Gaussian-like function for the gap on the imaginary frequency axis. So it's always in this form. Similarly for Z, we have something similar, but it's basically goes as 1 plus some lambda dependent value. For BCS system, you would set it to be 1. Now, if we have a weakly coupled system, we know that Z will have some lambda dependence. So it goes just basically 1 plus lambda, Z. And if we have a very strongly coupled system, well, lambda is very large, and then Z will go to 0, Matsubar term of Z. Well, in scale is basically square root of lambda. So now it'll become this lambda dependence of Z will become important later on. So like I said, we're also restricting ourselves to the Einstein phonon model. If we consider some other phononic model, then things would be a little bit different. So any questions at the moment? Okay. So we can now consider the superfluid density in this Matsubar formalism. Once again, we can consider the imaginary axis and real axis formulation. Numerically, we'll be doing everything on imaginary axis, but the real axis gives us some insight. And now we see the superfluid density is a function of this lambda electron-phonon coupling, as well as tau, which characterizes the impurity concentration or the scattering from impurities. And that's buried in here. So if we look on a real frequency axis, we can actually solve for the superfluid density in the BCS and Eliashberg limits. The BCS limit in Eliashberg theory could be, I don't want to say it's equivalent to taking lambda going to 0 and there's subtleties, and Marsiglio talks about this. But for now, we can take this system and consider the BCS limit. And what we see is we have this equation here at t equals 0. And then if we have a very clean system, this superfluid density will be 1. So the superfluid density is just unity, then everybody's in a condensate. But if we have a BCS system, sorry, a dirty system, where tau is very small, then it basically was pi delta naught tau. And this is still this term out front. So like I said, this just reproduces the work of Sung-Bo-Nam. Now, if we're considering an Eliashberg system, this delta naught is replaced by the gap edge, delta 1. And we've seen the dirty limit. Now, if we characterize this by gamma, where this gamma is 1 over 2 tau z, z1, sorry. And then the dirty limit of the superfluid density was pi delta 1 tau. So basically, it's analogous to Sung-Bo-Nam's work. We just replace delta naught by delta 1. However, in the very clean system, we no longer have 1. We have the superfluid density scaling as the inverse Z1, where Z1 is just the analog of the gap edge. It's just you can write down the effective gap, energy gap in Eliashberg theory as delta 1 plus I delta 2. This is just a real part. So we have the superfluid density now scaling as 1 over Z1. Like I said before, Z1 will have some lambda dependence, so we'll have some electron dependence on electron-phonon coupling strength. So for a strongly interacting system, the Z1 here will go square root lambda, so the superfluid density will actually be suppressed as we increase lambda, even in a very clean system. So this was a real frequency axis calculation and estimation. Now we can look at numerics, and we basically find what we predicted in a sense. So here, we look at the superfluid density, and we plot it versus lambda. And the color here denotes 1 over tau. So once again, blue is very dirty, and green is very clean. And I'll make it E here as the Einstein frequency. So the dirty limit, and this is on the log scale on a y-axis. So in the dirty limit, basically it will be significantly suppressed. That's not surprising. But in the clean limit, we actually see it actually goes from 1 to scaling as this dotted green line. This dotted green line is numerically found Z1. So we see that the analytical prediction, the dotted green line, is exactly on top of the clean result that we get from numerics, from iteratively solving these Eliashberg equations. So we've seen there's some lambda dependence now in the superfluid density in a clean limit. Now, this is half the picture of our ultimate destination, which is home scaling. We also need the normal state conductivity. Now, the normal state conductivity is given, we can also calculate the effect from these impurity scattering. And now we have a generalization of this Judah formula. Z2 here is the imaginary part of Z. Remember, Z equals Z1 plus I Z2. And then in this C here is some complicated function of lambda. The important thing is that we can consider the ultra dirty and ultra clean limits. So the dirty limit, this C just reduces to tau, and then we have the Judah formula for conductivity. So there's no lambda dependence anymore. Now, if we have the clean limit, however, we see that it actually scales as basically 1 over lambda, this C. So once again, as if in a very, very strongly coupled limit, we have a reduction, a suppression of the normal state conductivity right above Tc. So both the T equals 0 superfluid density and the T equals Tc normal state conductivity can be found for any lambda and any tau. And we can have a plot here where we look at the normal state conductivity just divided by this plasma frequency squared to make it unitless, and to put in nice units, and plot it versus lambda. Once again, the color denotes clean versus dirty. So this dashed green line is the clean limit from our theoretical prediction. And we can see that basically in this normal state conductivity, if we have a very weakly coupled system, it will diverge. This is known from Judah theory. But as we increase lambda, we have some upper limit now for the clean system. So very strongly interacting system in a clean limit will have some deviation from Judah theory. So we have lambda dependence now in a T equals 0 superfluid density. in Eliashberg theory. We have some lambda dependence now in a normal state conductivity um, in the context of Eliashberg theory. Now, let's look at home scaling in Eliashberg superconductor. So we seem to have some this residual interaction effect basically in these systems in a clean limit. And we want to try and get home scaling by some mechanism that's not just impurity scattering. And we want to see if we can get it actually from just strong correlation itself. Any questions at the moment? Okay. So once again, just flashing this again. The zero temperature superfluid density is on a y-axis. And this is BCS theory. And the normal state is on the x-axis. And we only see BCS home scaling in the dirty limit. We're going to plot things a little bit differently now. And we're going to plot the zero temperature superfluid density on a y-axis. Once again, a normal state conductivity times Tc and x. And the color now is lambda. Yellow here will be very strongly coupled. Blue will be very weakly coupled. And we're going to take little slices of 1/tau. So here, this is a single line in 3 dimensions. The extra dimension is coming out of the plane. And it's basically denoted by the color. And we see that home scaling or Holmes scaling is always valid in a dirty limit for all these lambda values. So, and this is very, very dirty. Now what I'm going to do is I'm going to take slices further and further, changing this 1/tau, going from the dirty to the clean limit. So now, as we go to 1/tau, going 1/tau omega e going as unity, as we go to in between these dirty and clean limits, home scaling is only valid, but in the weak and strong. So we see here in this intermediate region, we actually have a bend back. That was quite surprising. So we see that the very strongly interacting system will obey home scaling, and then intermediate values we bend back, and then it obeys it again for the weakly coupled system. And then as we tune 1/tau here to be cleaner and cleaner, it flips, and home scaling is now only valid in a clean limit in a stronger, strongly coupled system. So we've looked at it. Now we can see home scaling at certain lambda values, at certain tau values. We can now make a Holmes phase diagram, and that's basically shown here. So this is from solving from lambda going to about 0.3 to 100 for the gap in Z, solving these Eliashberg equations, and then calculating the superfluid density and a normal state conductivity for 1/tau, and then seeing where we have linear scaling. So the color here denotes the value of the Holmes slope. If it's white, this means that we no longer have linear scaling. So there's no linear scaling here or here. So now we will, so for example, here, this is the very weakly coupled clean system. And in the weakly coupled clean system, you basically have the superfluid density being unity. So no home scaling. Here, and this is the dirty BCS system, and we see home scaling is present. Here, we have a more strongly coupled system, and it be in the dirty limit. And here we have the cleaner system. And here we actually have the bend back. That forms this net here. So we see as we increase the electron-phonon coupling strength, we can then have linear scaling even in the clean system. So this describes when and where home scaling works in Eliashberg system, but we can take it a step further really, and we can actually consider other scaling relationships. So before Holmes, there was Pimenov scaling. With Pimenov now, instead of sigma Tc, it's sigma tau inverse. And we see that Holmes Pimenov scaling also appears in a strongly coupled system by virtue of very strong electron-phonon coupling. Rufus and I can also come up with our own scaling relationship, a Holstein phase diagram described by Leibniz Holstein phonons. And that's described by now we replace Tc by omega e. And once again, we see this scaling relationship emerge in a very strongly coupled system. So very strong interaction leads to these universal scaling relationships. Now, this leads to the question of, okay, we see, if I just go back here, home scaling emerging from this Eliashberg system. So what we had to ask another question of why this is happening. So originally, home scaling was proposed to be connected with Planckian dissipation. So in the strange metal, was suggesting that the resistivity going as linear T was connected to this idea of the transport scattering time going as basically h over kBt. So the fastest these particles could dissipate energy would be from this Planckian scale. And it was suggested by Jan Zanen that basically even due to some simple unit analysis argument, one could find that home scaling is intimately tied with Planckian dissipation, basically. So it was tied with its high TC physics. We can do the same thing here. We can consider the effective tau scattering time of the electron from these phonon effects and divided by the Planckian time and consider sub and super Planckian in behavior. And there is no correlation at all with the appearance or lack thereof of Planckian dissipation in home scaling. So there's no correlation with this figure in this one. So in our context, it seems to be there is no connection between Planckian dissipation and home scaling. This shouldn't be that surprising. We see home scaling in the BCS system as well. But basically, there's no connection to Planckian dissipation. So we had to ask now the question, why is Ohm's law being restored in a very strong interacting electron-phonon system? So we can consider these four different cases: the BCS ultra dirty, the BCS ultra clean, the Eliashberg ETH ultra dirty, and the Eliashberg ultra clean. Eliashberg theory is really not a theory of high TC. Even if we take lambda going to infinity, I think TC is really, really small still. So this is not an applicable theory for high TC systems. So let's try and understand what's going on here. Why are we getting home scaling? What does it mean? If it doesn't mean high TC, it doesn't mean dirty BCS physics. So we already talked about from the work of Sang-Nam and just 1960s electromagnetic theory of superconductors that the superfluid density will go as 0.8825, basically calculating the slope, basically delta over 2TC times TC sigma. In an ultra clean system, the superfluid density is 1, no home scaling. In an ultra dirty limit, we can calculate the home slope and we find something similar to the BCS. But now basically the value of the slope is replaced by the real part of the gap at an imaginary axis, the n equals 0 component. So this is not necessarily this nice value here. It's going to be something a little bit different. So the slope is going to be different from the BCS. But this is just basic consequence of the form of the T equals 0 diamagnetic response and DC conductivity. So this is also talked about in the, I think, 60s book by DeGennes on superconductivity. So this also dates back quite a while, as well, quite some time ago. And there's some interesting physics in the ultra dirty limit, which I'll show in a few slides. But for now, let's just focus on the clean limit, when this is really different from BCS. So in the clean limit, we can also do a calculation. We find that the Holmes slope now, superfluid density T equals 0 and a normal state conductivity times DC. Now the slope is given here. Well, now this lambda is electron-phonon coupling, and this I term is just an integral. It's integral that goes to 1 in a very strongly coupled limit. So this is lambda over 1 plus square root lambda. So when lambda's in these intermediate values, there's going to be some weak lambda dependence, but basically we have this linear scaling. And this is a consequence of non-Galilean-invariant. So why? Well, in this recent work, why we get home scaling in the system is due to the fact that the superfluid density scales as 1 over z. The 1 over z dependence is what contains this electron-phonon coupling. This 1 plus square root lambda is where this lambda dependence comes into play. And so all the home scaling we get in the system is because the superfluid density to the clean limit in Eliashberg system goes to 1 over z. And this is only applicable if we have an Einstein-Phonon model. It was shown from recent work by Chupakov and his grad student Zachary, Andrei Chupakov, that if you have this, he describes these systems as effectively Galilean invariant and non-Galilean invariant. So if you have some dispersive, if you have some non-dispersive phonon, some Einstein phonon, this would be a non-Galilean invariant system. The Einstein phonon just acts like some impurity, scattering or the electrons can scatter off of. And we have no electromagnetic vertex corrections in the calculation of the superfluid density. So it's just purely 1 over Z and then the superfluid density. If we have a dispersive phonon, not a non-Einstein boson, this would be interpreted as an effectively Galilean invariant system. And so then you can have some Galilean invariance, and you have some electromagnetic vertex corrections, which exactly cancel out the 1 over Z term, and then we restore it to 1. So in this context of Andrei Chubakov's work and also Tony Leckett's work that also describes this superfluid density dependence upon being unity or not due to the dependence of the Galilean invariance, we can interpret that what we need for home scaling in the Eliashberg system is for the superfluid density to not be unity. It has to scale as this coupling strength. It has to go to 1 over normalization to 1 over Z term. And that's equivalent to saying we have some breakdown of Galilean invariance. So we could have it in the dirty system, in the BCS dirty system, we also have the breakdown of Galilean invariance by virtue of electrons scattering off of impurities, some elastic scattering, some Judah-like scattering. Now, in our Eliashberg system, we would have something similar, but in a strongly interacting system, we can also have a breakdown of Galilean invariance that gives us a non-unity superfluid density by virtue of localized Einstein phonons. Electrons scattering off these localized Einstein phonons inelastically. And then the superfluid density is no longer unity, it's 1 over Z, and then we get home scaling. So basically what we can say is that some diffusion mechanism, some either elastic scattering from electrons and impurities and elastic of electrons and Einstein bosons, is necessary but not sufficient ingredient for home scaling in general in these Eliashberg systems. It's necessary but not sufficient because we have that backbending term, right? So it's not necessarily insufficient, but it's a crucial ingredient basically to get it. Like I said, this is to the best of our knowledge the only theory of home scaling beyond BCS physics. So there is no other theory of home scaling beyond dirty BCS physics, to our knowledge. And we found this in the context of Eliashberg's theory. We found that home scaling works for larger values of lambda, even in the clean limit. But the catch here is that home scaling breaks down in the clean limit for very, very large electron-phonon coupling. So A to H, the home slope here, scales a screw at lambda. So as lambda goes to infinity, home scaling is lost in a clean limit. So now we have to ask the question of then what happens in a dirty limit for a very, very strongly coupled system. Okay, it looks like I'm doing fine with time. So in this dirty limit, we want to ask the question what happens in a very, very strongly coupled limit, because in a very, very strongly coupled limit is asymptotically strong electron-phonon coupling, and this asymptotically strong Eliashberg theory, we have universal physics emerging. Before I continue on, any questions? Okay. So asymptotics basically means this universal behavior. So here, lambda, which I was talking about before, was the dimensionless electron-phonon coupling. We can also talk about lambda equals alpha squared over omega e squared, where alpha is a unitful electron-phonon coupling. And if we plot an Einstein-Phonon model T out of alpha versus omega e of alpha, we see that what's important is that as alpha goes to infinity, we have universal behavior and appearing, a very special theory appearing, and very, very strong coupling. So this is some toy phase model, the phase diagram one can draw, where now this dashed blue line denotes where we have superconductivity, and this is the phase transition. And then we've seen that actually as alpha goes to infinity, and as TC goes to universal value, which is actually the famous Allen-Dynes result. and that T is connected to square root lambda times 0.1 and 8 omega E. So we have universal physics appearing in asymptotically strong electron Eliashberg theory, and now we want to ask, well, do we have universal behavior in a home slope appearing in asymptotically strong Eliashberg theory? So like I said before, the point is not now we are trying to describe, say, lead or decuprates witness very, very strong lambda, and that's not what we're doing here. We're using Eliashberg theory as a case study to find home scaling in a system not by virtue of impurity scattering, but just by virtue of strong interactions. And we're taking lambda going to infinity here to see what the upper bound is on this home slope, what it could be. So, as I said before, in a strongly coupled theory, we have universal physics, like the Allen-Dines result of TC, which is denoted here as A omega E squared lambda over 2, where A is some constant, 0.256. We can rewrite the Eliashberg equations in this unitless form, where we divide by square root lambda here. So now it's lambda dependent. We can do the same calculation, and we can check it analytically too, and numerically, and we find it in the home slope in the ultra dirty limit. Basically, sorry, in the ultra strong limit. In the clean limit, we have some residual lambda dependence as expected. So then is no home scaling. But in the dirty limit, we actually see it goes to a constant term. It goes as 1 over 3 times 1 over A, which is 1 A is defined here. So the home slope in a dirty and asymptotic limit approaches a universal value of 1.33. So the home slope here in a clean limit, as I said before, we have some divergence. So home scaling works in a clean Eliashberg system, but it's intermediate values of lambda, but not as lambda goes to infinity. But a dirty limit, it will still work in the very strongly coupled limit. But now the value of the slope is changed from this 0.8 we saw before. So we can now consider the whole spectrum of the home slope from BCS theory to asymptotically strong, any one of a tau, for a tau in the dirty limit. So we see here the result of some numerics and our theoretical predictions. The BCS home slope will basically be equivalent to lambda going to 0 in this context, or basically so. And we see that it approaches this value of 0.88. And as we increase lambda, we did this for different values of 1 over tau. And once again, blue is dirtier. And we see as we go dirtier and dirtier, we collapse to this value of 1.33 or so. So we see in the ultra dirty limit, the home slope will then go from the BCS to the asymptotically strong value 0.88 to 1.33. Now, what's interesting is that there's some work on Combusco, which suggests that in the context of Eliashberg system, the Einstein-Phonon model is universal. So the Einstein-Phonon model is the universal theory in asymptotic limit for Eliashberg theory. So our result, this 1.33 for the asymptotically strong home slope, puts an upper bound on the dirty home slope for any Eliashberg, any system described by Eliashberg theory. So in a dirty system, you can't get any stronger than 1.33 if it's described by Eliashberg theory, no matter what the underlying phonon propagator is. So this is really this universal result that if it's described by this theory, it will just be the upper limit. So now we can recap what we talked about. So the home slope here is really was considered a mystery for, I think, quite a number of years in the context of these cuprates and for other materials as well. Excuse me. So, like I said, it was empirically known, experimentally known, and there's a scaling relationship for many different materials, even BCS superconductors, it's technically known for, but people weren't really sure why. And what we provide is really the first theory of why home scaling would emerge, not by virtue of dirty BCS physics, but purely due to strong interactions. And we showed this in the context of Eliashberg theory. So we can get home scaling purely by a strong coupling, some kind of strong coupling. And we can consider the clean and dirty limits. And we get it in a clean limit, but only for intermediate values of lambda. As lambda gets very, very strong, then this dependence will become too strong as well, and we lose it. In a dirty limit, however, we obtain home scaling still, but now it's quite different, a little bit different from the BCS result. So, and this result gives you, like I said, an upper limit to the dirty home slope for any system described by Eliashberg theory. Similarly, we also talked about these the Pimenov slope and a Holstein slope in a very clean, strong coupling limit. So in this context, we also get other scaling relationships true in these other universal scaling relationships by virtue of very strong electron-phonon coupling. So we really get this universal physics emerging. And like I said, what's really important about this work is that the problem of home scaling in Eliashberg theory has been pretty much solved in this context. We go from lambda going to 0 to infinity, basically, in ultra dirty and ultra clean limits, and we see exactly when and where this home scaling can emerge. And we find there's no connection to a very high TC, but instead we have to have some effective diffusion mechanism, either through some scattering off of some localized Einstein boson, or we have to have some purity concentration, some finite impurity concentration, and then like a BCS-like model. So now it's basically the story that I want you to take away from this is that home scaling is, we don't attempt to describe what's happening in the cuprates. We'll just give a case study where home scaling can emerge by some mechanism that is not dirty BCS physics. And we solve this in the context of Eliashberg theory. And thank you for listening.
All right, thank you, Joshua, for a very nice talk. The session is now open for questions. If you have questions for Joshua, please feel free to unmute yourself and go ahead.
I have a question.
Yep.
So in your model, you only consider phonon. And how about, I'm just curious, how about Moray-Anderson like a potential? Would that change some of your predictions?
So you're thinking like a twist, like a more, so you're thinking
Like
like
adding this Coulomb pseudo potential,
what potential side?
the Coulomb pseudo potential.
Yeah, so if
Moray-Anderson.
you include some Coulomb interaction, we believe that it won't really change the result that much. We're still finalizing some thoughts on this. In terms of changing the underlying propagator, we're still thinking about this a little bit.
And also, you okay, probably because you consider Einstein phonon, so you can write like a pure frequency dynamical theory. Otherwise, like in general, you need like a spatial resolution, and I imagine that that's actually a very difficult problem. Yeah.
Mhm.
Okay, thank you.
Yeah. So that's a good question. So I mean, like in the context of Eliashberg theory itself, and then really we think that Einstein phonon would be the only example. If we go beyond Eliashberg theory, then that's not really described in this work, so that'll be future work. Yeah, any other questions?
All right, this is Adrian. I got a very naive question.
Mhm.
Why is it reasonable to consider tau and lambda as completely independent quantities?
So, well, lambda comes from the spectral function, the phonons, right? So I think that would be in general independent of tau, and then tau would just be some external term that one would get from. So, for example, if I go back, let me try and find this. So one would have some. Sorry, later.
Yeah, so lambda is an intrinsic property of, it's just parameter in the Hamiltonian, let's say, right? But about tau is phenomenological, right? So
yeah, but tau will be intrinsic to, like, say, the impurity concentration in the material. So I mean, okay. I guess there might be some example of a system maybe where there might be some dependence on lambda and tau. So maybe one would have to go to like some work that considers like this first principles, integrating it into like this Eliashberg work to actually see how tau and lambda might be coupled. I'm not familiar with that completely, but maybe in some exotic material one could explicitly calculate that, but I'm not familiar with that. In general, people take them to be independent, but there might be some contexts where they would be coupled together, but I'm not sure.
Perhaps I could comment.
Yep.
That I think what Adrian says is correct, but the Eliashberg theory takes into account the scattering due to the electron-phonon interaction. So by including the tau, as Joshua's done, he's including like impurities, and there's an effective tau which combines the two. So in fact, he's got scattering in there at a, you could say, at a more microscopic level for the phonons, and at a more phenomenological level for the impurities, or whatever it is that's causing scattering other than these phonons.
Gotcha. I understand. Thank you very much. Yeah,
Sorry,
there's another question?
Yeah, I have a question. So yeah, my understanding is when you take the Ohm's law and put it again with the Uemura, Janen did this beautiful work where he get this very fundamental relationship between TC and then a scattering rate, which is similar to the Heisenberg relationship. So my question is related to the previous question. The tau, because you can get a tau from the phonons or another tau which is independent. So which tau, when you put everything together and you do the same scheme of Janen, which one do you have to take?
So when I consider like this plot of tau.
So for instance, Janen because if I remember correctly, the argument, the Ohm's law is very important because you arrive to this very important relationship where you have TC and then the scattering rate, which of the order of H bar. That's one of the most incredible relationships that you are.
I see, yes. So here so this is the total tau. So this includes
the Planckian, exactly.
Phonon coupling. Yes, exactly.
That's what I was curious. So which one do you take? You take the total one. So you
the total. Exactly.
Okay, thanks.
Yes.
That's beautiful. Okay.
Okay, thank you. Any other questions?
So I have one.
Yep. Who's that?
Yeah, so Joshua, thanks for a great talk. I remember you talking about this while we were at Dartmouth, kind of piece by piece as it was going along. So it's great to see the whole thing come together. So maybe I have a simple question since I don't work on this kind of thing. In terms of, have you thought of kind of maybe novel ways of enhancing this lambda value? So I think you mentioned it's limited to kind of 4, but is there any work to kind of, I don't know, use light-induced techniques or anything like this to significantly enhance the range that you can explore inside materials?
Yeah, I've been thinking about this a little bit, how one could use some like exotic light source maybe to enhance lambda. I'm not 100% sure. I mean, the work that really limits, I mean, it's been a number of works that sort of limit lambda and some different suggestions. Some people believe that lambda is limited by 0.5. Some people believe it's limited by 3.78. And there was this work, I think, by Sebastian and company, which sort of talks about it being limited due to this free energy analysis. And there's other people who believe a lambda can go up to infinity. So I mean, let's say that it's like limited by 3.78. And then more than likely, you could, I mean, I would say more than likely, but there might be a way of doing it with like you drive the system, and then you could effectively increase the lambda. But the problem is one would have to like very carefully or consider how the Eliashberg equations themselves change, right? So I think it's just a complicated question. I think it might be able to be done. I haven't really seen any in particular. There's actually now I remember, and there is some work and actually talked about like observing the Meissner effect. in a driven superconductor at a very, very high temperature. So this won't be Eliashberg, but it might be a way of something equivalent, like you see a very like a Eliashberg theory working at a higher effective electron-phonon coupling under some drive. But I'm not really familiar with any work at the moment, but I'm sort of thinking about this.
One simple clarification. So you say that you find a universal slope in the strong coupling limit, but the experimental data seems to fall indeed on almost on a single straight line. But here,
yeah,
plot shows that the slope can vary, right, depending on the electron-phonon coupling. So
okay, good.
you,
So you can see it varies from like 0.88 to 1.33.
mm-hmm.
So here you can actually see, so if you look at the data, there is some leeway here. This is also in a log-log plot. So it's actually like it's not a completely one-dimensional straight line. There's some error bars here.
Mm-hmm.
So one were to consider some like effective theory for these materials or for these materials, there might be some like small variation of the home slope.
Mm-hmm.
And that would be included here, for example. So it's not like a completely one-dimensional line, it's some leeway.
So the slope can vary within the gray area and okay.
Yes. Yeah. So you can see in this one these different materials, right? So like this one, this
certainty on the slope. That's the important question. What would be now at the moment that you think? What is 1 point, for instance, the one that you show 1.33, it is a realistic value, or?
So the 1.33 is absolute upper limit for the dirty system to have home scaling. So I mean, you go from 0.88 to 1.33. So I mean, you might be able to see some variation as you for the like lambda equals 4, but not really. So one would have to maybe consider like some protocol and Andrew considered, where one could maybe have some material where you increase the lambda to actually see this deviation to home slope. Or maybe one could consider if one like keeping lambda constant and then changing tau, right? Going from a dirty to clean superconductor. Maybe and then one could also see some variation of the home slope as well. But one needs like a knob to tune, right? So the knob could be one consistent knob. So one could tune tau, one could tune lambda. If you tune lambda, like I said, it's quite difficult and you might be quite limited with conventional methods. So maybe the easiest way is actually just consider tuning like tau, going from dirty to clean superconductor.
Thank you.
All right. There are no other questions. We thank Joshua one more time for a very nice talk, and I hope to see you again next week. Bye, everyone.